The discussion topic is voltage and current reference. In the previous classes, you have learned how to design operational amplifier either in voltage to voltage conversion mode or voltage to current conversion mode. In any building block of large scale integrated circuits, suppose you are going to design a big IC. There are suppose large number of amplifiers. Let it be gain of A1, this is A2. Suppose these are voltage amplifiers, some current amplifiers be there, G1, G2. The important thing is to set the circuit characteristics to the desired A1, A2, G1 and G2 values is to set the biasing points of the circuits. That is, you are to bias the circuits to a particular level. Okay. So biasing the circuits means there are two forms of biasing. One is current biasing, another is voltage biasing. Suppose in operational amplifier, you have learned that you are operating the circuit in this mode, and here you are applying a bias voltage here, right? This is some internal bias DC voltage you are applying. Again, when you look for the internal circuitry, suppose this is you want to implement a current mirror. When you want to implement a current mirror, suppose there lies your actual amplifier circuit, and you need to set proper ITEL here, right? So you need to design a circuit which will fix a particular current reference. So we will deal with these two particular elements. One, to design the current reference, another one the voltage reference. So this is the main objective of this course. There are a few factors which generally affect the circuit designing properties. The important thing is the temperature, that is different process parameters, like for example if you just consider mobility, electron and hole mobility, this is a very much temperature dependent parameter. So when you will go to design a voltage or current reference circuit, you should fix the goal that over a wide temperature range your designed voltage value or your designed current value should remain fixed over a wide temperature range. Suppose you operate the circuit at 27 degrees centigrade or minus 27 degrees centigrade, there will be no variation in voltage or current level. Then actually in practical case there occurs some deviation, but we will later discuss it. But your target is to fix the voltage or current level fixed over a wide temperature range. For example, in case of operational amplifier, you just represent a current mirror in this way to set the tail current source, or you route the current through this way to second stage or first stage, whatever be the number of stages. Now suppose you just eliminate it and put a resistance here. What would be this can set my current to this path, that is 1 by Gm of this transistor, and R, that is VDD divided by R by 1 plus Gm, that will define my current. Okay, but there are few constraints. Suppose these are, suppose you want to make the current over a wide, suppose for your design aspect you have to design a current for some cases 100 microampere, in some cases 10 milliampere. So to support this amount of variation in current, there should be large amount of variation of this R. Again, this is very much dependent upon whatever the supply voltage you are applying here. Okay, so we can fix our objective to design a current reference independent of this VDD. If we can make this, then whatever beta VDD, then we can generate any value of current. This is our primary objective, to make the generated current supply independent. Okay, now I am just drawing a structure. Okay, if we set the ratio of this transistor and this transistor 1:1, again this one and this one 1:1, whatever be the current through these two paths, you can say that these two currents are equal, right? If this is I1, this is I1. Okay, another important assumption that you can carry out, the voltage at this node V1 should be equal to voltage at this node V2. Okay, how you can prove this? Let for example V1 be greater than V2. Okay, if V1 is greater than V2, that is if V1 is high, this I1 will be less, that is current through this one should be less than current through this one, I2. So this one less than this one means current through this transistor is less than current through this transistor. Okay, so this, that is if this is I1, this is I2, and this is I2 prime and I1 prime we write, then what happens? I1 prime less than I2 prime, right? Then I2 prime makes a larger voltage drop across this transistor. This will lead to V2 greater than V1, right? So this is a contradiction. So these two voltages must be at same level if these two transistors are ideally matched. Okay. So one thing that is clear from that, the current through these two branches are equal. Okay, but you can't determine what is the amount of current that is flowing through these paths. So here we propose this is a structure where, for example, let be the current through M1 be IDS1, that should be half K dash W by L of 1 VGS1 minus VTH1 whole square, if we neglect the lambda effect, right? Again IDS2, that should be equals to half of K dash. Here you can see here the ratio between these NMOS transistors are 1:n, right? And here is an introduction of resistance here, right? But these two transistors are set 1:1. Like from the previous case, here also V1 and V2 should be equal. Okay, so we can write the current equations like half K dash N W by L2 VGS2 minus VTH2 minus the drop across the resistance, that is IDS2 multiplied by R whole square, right? So from this IDS1 and IDS2 should be equal because this M3 and M4 are kept 1:1 state. So we can just say these two values are equal. Okay. So this W by L2 means N into W by L1, that is ratio, this ratio, and so just divide these two, it would be N now. If these VTH1 and VTH2 are assumed to be equal, if we assume this, then from this equation, like and if you just go on solving it, there is another constant, that is another available thing, that is V1 equals to V2, and if you just solve it, that is then you will get VGS2 minus VTH2 should be equal to VGS1 minus VTH1. So this leads to IDS2R divided by VGS1 equals to 1 upon root n. Then IDS2R, that is equals to 1 minus root n multiplied by VGS1 minus VTH1. Again you can write from this equation VGS1 minus VTH1, that is equals to root over of IDS1 divided by half Kn dash W by L1, right. So if you just solve it, you will get this current equation here, IDS1 equals to IDS2. So these two are equal, and if you just solve it, you will get this current expression, right. But there is a question, is the loop is at all stable, the first one, and second one is how the circuit works when we just when we switch on the power, how it will starts working. One thing is that you can say if both the currents are 0, that is IDS1 and IDS2, the value of both the currents 0 is a solution of this circuit, you can say it. If both are 0, IDS1 equals to IDS2, so both of them can be 0, this is one of the solutions, but you need to fix it to any one particular value, right. So how this will work? This is my circuit, okay. Now you switch on the power, let initially it was 0, now put it to VDD, okay. At the initial stage all the currents through the transistors are 0, okay. So in this expression there is no expression of VDD, right, no VDD is there. So only change in VDD will not cause current to flow through these circuits, right. So at the initial stage when you just power on this supply, in some artificial way you need to introduce some amount of current through the circuit, okay. So this will, when if you can inject some amount of current through the circuit, then it will balance itself, okay. So some circuit you have to design which artificially introduce some amount of initial current, okay. That circuit is called startup circuit, how you will design it? Okay, so I am just explaining how does it work. You just introduce a PMOS here and two inverters along with this PMOS and resistance combination. Okay, at the initial stage all the node voltages and currents are 0. Okay, now you are powering on the supply. At the initial stage the current is 0 through this path. Okay, you can find here this PMOS and this PMOS, they are mirror connected, right? So at the very initial stage what happens, if the current, it is very small amount of current through, almost negligible current is flowing through this path, so current through this PMOS device again very small, right? So there would be very small amount of voltage build up at this node, that is the IR drop, right? You are powering on this VDD in this way, this voltage will rise some amount in this way. Suppose the threshold voltage of these digital circuits, like this is the threshold voltage of the digital circuits, but this is quite below the threshold voltage, so this would be 1, this should be 0. Okay, now this 0 voltage is getting applied to the PMOS input, right, and this PMOS is being powering on. What happens, this is very much conductive, right? So once this VDD is powered on, this injects a current through this path. Okay, now this amount of current that we introduced at the beginning, now once the current starts flowing, current will flow through this path also, again this will mirror current through this path here. So what happens, this voltage builds up, right? So it crosses the digital threshold voltage here. So once it crosses the digital threshold voltage here, this goes to VDD. So input to the VDD just switches off this PMOS device. Okay, the circuit now balances itself. So introduction of this circuit only to introduce a small amount of current to this circuit, to this current branch, so that the circuit can stabilized at its required IDS value. Okay, next thing is that, is the loop stable at all? That is, if some amount of perturbation exists here, does it circulate through this loop in a regenerative way? That is, we have to analyze whether this loop is stable or not. Okay, for this analysis, let me break the loop here. Let this is V1x and this is V1y. Okay, we will observe what is the gain from Vix to V1y to V1x. What is the gain here? Oh sorry, there is a resistance here. Resistance here. The gain is here. that is GM2 multiplied by 1 upon GM4. Here this is a load and source degeneration resistance is here. So it would be 1 plus GM2 multiplied by R. Okay, gain from this node to this node. Again, gain from this node to this node, what it is? GM3 divided by, that is multiplied by, this is the load 1 by GM1, that is GM3 divided by GM1, right. Now GM3 and GM4, these two are equal. This one M2 and M1 are, this is 1:n, right. So the ratio of GM2 and that of GM1, that is GM2 should be equals to root n times GM1, right. This square root of I, okay. Then you can say it GM2 is root n GM1, again this is root n GM1. So what is the gain? Loop gain here, root n GM1, this GM1 cancels, 1 plus root n GM1R, right. What is GM1? Twice Kn dash W by L1 multiplied by I. So you have get the expression here, expression of I. You just put the expression of I here. This is 2 Kn dash W by L1, I means 1 upon R square right. So this one cancel, 2 by R, 1 minus 1 by root n. Then GM1 multiply R, that is equals to 2 1 minus 1 by root n, okay. So you can find here. So what would be this root n divided by 2 root n minus 1, that is equals to 1 by 2 minus 1 upon root n, right. N is greater than 1, so this loop gain is less than 1. So this is not a positive feedback at all. If any noise or any kind of current or voltage disturbance appears at this node or any node, it will get diminished, it will get suppressed, not regenerative. Any questions for it? There is another type of configuration, that is, you can see here this configuration. You just draw the circuit and analyze whether this loop gain is stable or not. I have given the expressions, okay. You just try to analyze in terms of these expressions, like this circuit, whether this, there is interchange of resistance, yes, this is R goes to here with the diode connected device, okay, and just try to write some equations and analyze this loop gain is coming or not. You can find here this loop gain is 2 minus 1 by root n. If n is greater than 1, then it should, loop gain should be greater than 1, right. So this is a unstable loop here, so you can't use this circuitry. If you just go on DC analysis of this circuit, you will get the same type of expression, but in terms of AC analysis, it will not give a stable loop gain, okay. Any disturbance appearing at any node will become regenerative, and any of the current branch will get stuck to a particular value. You can't never change it, okay. Oh, there are some, these signs are actually proportional sign, okay, so they are not coming. In this context, I will discuss two important things. Those are required to design bandgap circuits. Okay, the temperature independent voltage reference circuit. One is called a negative temperature voltage, negative temperature coefficient voltage. This is a simple bipolar device current equation you can find. Okay, I have shown all the parameters like the saturation current, the Ni, mu, all these uh, all these components are expressed in terms of temperature. Okay, so these are some standard expressions of mobility, intrinsic concentrations. All those terms are represented in terms of temperature. Okay, so with change in temperature, this current itself changes. So all the parameters are very much dependent upon temperature, and if you write the what is the gradient of this equation, that is del VB del T, it bears equations like this. If you just put those terms there and solve it and go for the expression del VB by del T, you will get this expression. Okay, and you can find this gradient itself is dependent upon my nominal base emitter voltage and nominal temperature. So these two dependent parameters always stay there. Okay, so from observation at T equal to 300 Kelvin and VBE for 750 millivolt, this temperature coefficient, it comes around minus 1.5 millivolt per degree Kelvin. Okay, so this is a negative quantity. Okay, so that's why it is called negative temperature coefficient. In connection, there is one more term that is called positive temperature coefficient. Positive temperature coefficient, this states that if two identical BJTs, if they are operated under two different currents, if we bias the BJTs at two different currents, and if we assume the base currents are negligible, then we can state that the difference between this base emitter voltage is a function of temperature. This is the standard, I have written the standard equations, and you can find here this Vt equals to ln n. Okay, n is a multiplying factor. So this gradient of this voltage difference, you can find here, this is k ln n by q. All the terms are positive here. Okay, clear this is? So this term you can consider, this you can say is a positive TC voltage, positive temperature coefficient voltage. So negative TC voltage and positive TC voltage, you can use both these two to form a temperature independent voltage. Okay, so you can write that, suppose you design a reference voltage Vref, if you write in terms of, that is positive temperature coefficient like a BJT base emitter voltage, that is shown here, this alpha of VBE plus beta of Vt ln n. Okay, then if you take the variation of V reference with that of, with respect to variation of VBE with temperature and Vt ln of temperature at a particular nominal temperature, these two terms will sum up and give 0. These two terms will sum up and give 0. So you can say this reference voltage becomes temperature independent. Okay, so how you will make this reference voltage independent of temperature? Here is a circuit. You can say, for example, let it be R, and they are operating under same bias current, and you just go on adding n number of devices in parallel. Okay, so if we can force the voltage at this node, say V01, and voltage at this node V02, okay, then we can tell that the current, then we can tell that the reference voltage what we are getting here should fulfill the requirement of temperature independent voltage. Okay, so these two node voltages somehow we have to make fixed at particular level. Okay, so that's why an op amp is introduced here. This op amp, if it satisfies all those op amp characteristics like high gain, high input impedance, low output impedance, and small offset, then we can assume that the voltage at this node and voltage at this node, they are equal. Okay, and output of this voltage, so this is mind, this is not the supply. Supply is applied to the operation amplifiers. Okay, this is the output, and if you solve this, you will get the output at this node V out, that should be equals to VBE2 VTLN, that is the difference. And as we have introduced this R1 and R2 circuitry, this will lead this type of expression. Okay, the expression of V out comes like this. Now just compare it with this equation. You can put alpha to be equals to 1. Okay, and for beta, if you choose this 1 plus, that is 1 plus R2 by R3 multiplied by ln n equals to 17.2 and take the derivative with respect to t, then it will give exactly 0. Okay, you have to set ln n R2 plus R3 by R3 equal to 17.2, and if you take the derivative, this positive term and negative term will cancel out. Any confusion? So from this equation you can choose a particular value of R2 and R3 and number of parallel devices here. For example, we can set n equals 31 and R2 by R3 equal to 4 to get this expression value to be equals to 17.2, right. So this is, in that case we can say that this reference voltage is independent of temperature. Okay, now again one thing comes, there are two loops, right. Is the loop stable at all? You can see here a positive feedback loop and there is a negative feedback loop. Again, if the positive feedback loop becomes dominating, again some static problem may arise. So you have to make ensure, that is, first you just solve it. See, this is the feedback path. So here actually this beta p equals to 1 by gm1 divided by 1 by gm1 plus r1, this feedback factor comes here. Okay, again from this node this feedback factor is 1 plus gm2 plus r3 divided by 1 plus gm2 plus r2 plus r3, right. You have to make this beta n at least twice as that of beta p, so that this positive, that negative feedback loop always dominate. Okay, so this is the one criteria. While you go on designing this circuit, obviously come some design issues, like in this analysis we have assumed that this IC itself is not proportional to absolute temperature. We considered this IC to be a fixed value, but in practical case it may happens that IC itself is a function of temperature. Okay, and from this circuit you can find the current through this path is flowing through, that is the what is the voltage difference from here. Voltage difference is Vt ln n here, okay, that appears here. So current flows through Vt ln n R2 plus R3 R3, sorry, the current flows through, that is Vt ln n divided by R3, okay, here it is. So the current itself is proportional to absolute temperature. The current is Vt ln n itself is proportional to absolute temperature, okay. So if this occur, we can't write the expression in this way because IC itself is variable with temperature. So you have to analyze in different way, that is del Vb, that is variation of Vb with temperature is a function of Vt changing with temperature, IC and Is, all of these, okay. And if you consider this del IC by del T to be equals to Vt ln by R3T, that is directly comes from this equation, that is a consideration only, then this expression what appeared here, del Vb by del T, then Vb minus 4 plus m terms, that only get changed approximately to 3 plus m, okay. This is a purely observation. If there is change in of the collector current, then this del Vb by del T changes with this 3 plus m parameter, okay. This is just you put the different terms by differentiating and you will get this term. Another thing that may happen, that is we have considered the offset of the operational amplifier to be 0, but in case it may appear that there is some high value of offset voltage between the two terminals, it may appear, right. So this term will get added up with the output voltage. Another thing is, if the output impedance of the operational amplifier is not small enough, that is if it is greater than this R1, R2, R3, these values, again it will cause loading problem. So these things you have to keep in mind, that your op amp should have very low output impedance, very high output impedance and very small offset. So you have to make, so here actually if any offset occurs, that final expression will become like this, right. So you have to minimize the offset voltage as small as possible, so that the operational you have to make operational amplifier gain very high, so that this offset voltage is very small. Now the next thing is why this circuit is called band gap. The reference voltage expression is bears a form like this from here, bears a form like this. So if you put capital T to be tends to 0, what happens? This reference voltage will tend to Eg by Q. This is the band gap voltage of silicon itself, right. So at T equals to 0, this reference voltage is equals to the band gap voltage. So this is the significance of the term band gap, okay. This is the last thing, that is you have designed a current through this path, right. This I2 from the expression here, that is Vt ln n. You can use the same current to design a particular reference voltage, okay. This I2 is equals to Vt ln by R2, right. Here we just add a current mirror. So whatever I2 is flowing here, this one will be same current I3. This will cause a voltage drop across R3, okay. So if we put this Q3 and Q1 to be at same size, then the output voltage would be the voltage drop across R3 and this VBE drop. And this VBE drop is equals to Q1. Okay, you see here this I3 equals to I2 is equals to VT ln N by R2. This is my positive temperature coefficient. Okay, and VBE1 that itself is a negative temperature coefficient. Okay, so for room temperature is at 300 Kelvin, and if you just change suppose this 300 Kelvin to suppose 320 Kelvin or 280 Kelvin, like so, the variation is not, there is very obvious, there is variation, but variation is not too much. If you just take VE1 or R1I3 itself, the variation is very much with temperature, but here variation is not too much. If you just plot this reference voltage over temperature at particular temperature T naught, you can find there, you will get at T naught, you will get the exact reference voltage value what we want to design, and at T greater than T naught or less than T naught, you will get a gradient. Okay, so this thing have to keep in mind, that is when you are going to reference generator reference, if you just put it in terms of any band gap, any base emitter voltage or any voltage drop across resistor, this temperature coefficient is linear, this temperature change, right? And you have reduced this linear dependency with temperature with a small curvature. That curvature will always remain. So you can state that the voltage value what you are getting here to be a reference voltage of a particular circuit. Okay, and you can use, suppose this particular circuit, suppose this is the V out, you put the building block here and you can use at the input of the op amp. Okay, right? So this is the generation of my reference voltage. Again, from this circuit where we have designed a particular current reference, let for example, here is an op amp 1, this is op amp 2, and this is the differential structure. You can just this is my differential stage. I know this current here, this is a fixed current, this is not variable. Just set the W by L ratio of this transistor and W by L of this transistor to a proper value, some 1 is to N1 and some 1 is to M1, N2. This will give my proper tail current values to the lower transistors. Okay, so these are the way how you can design the current and voltage reference. Clear it is? Any question? No question? Okay, that's all.